Very good. And then we have the second talk for the afternoon session. We welcome Fernando Marchesano for asymptotic curvature and interacting gauge theories.
Okay, thank you. Hi to everyone. It's a huge pleasure to be here. Let me thank the rest of the speakers let me join the rest of the speakers by thanking the organizers for this very nice conference, for the invitation to give a talk and the opportunity to present my work here. Indeed, I will be talking about some recent work that has to do with the asymptotic curvature in moduli space. It's mostly based on this paper that appeared end of last year, together with my students Luca Melotti and Lorenzo Paoloni here in the audience, and in some follow-up works in collaboration on one hand with Luca Melotti and Max Wisner, also here, and then with Lorenzo and Alberto Castellano, and that I will talk about time permitting. But before I start, I really want to thank the organizers for something else. I'm well aware that they have made a huge effort to have the conference in here instead of DESI, for instance. That would be much easier in terms of money, effort, organization, fire regulations. So I know we do this at the end of the conference, but I don't want to wait. I will propose an applause for them because they really made us enjoy to be here in these surroundings. So thank you. But I'm not done yet. Actually, I want to thank them for something else. Because today I realized that there's something really important going on in this conference in terms of the lifetime of the conference. I don't know if you noticed, but there's something that is going on for the first time ever since this conference series started. Anyone? No? This year, for the first time ever, we managed to keep the same conference name for 3 consecutive years. Wow. Wow. I mean, that maybe the younger participants wouldn't appreciate it, but if you, I encourage you to go to the webpage, to the past conference tab, and check the names. And then you will see that they have been changing the name more often than you change your underwear, okay? It's crazy. It's kind of a tradition of the conference series. And it's not even a long name, right? Like 2 words, 3 words. There is not so much degrees of freedom, but they manage to change it every 2 years or more. But this is over, thanks to the organizers in this year. We have reached a milestone in which we have the same name for 3 years, and this has given the conference a sense of solidity and seriousness that we really need. We are in the right track, and that's what is really important. And I want to ask another applause for them for making this possible. Yes, yes. I know they have really deal with the temptation of changing the name to becoming creative. So whoever is coming next, I'm not looking at anyone, but whoever is coming next, I have a message: please be strong. Don't succumb to the temptation of changing again the name. But if you do, if you're not strong enough, please let me know because I have a few ideas. Okay? So let me begin. What I want to tell you today has a common root that you have already heard about several times in this conference, which is the distance conjecture in the context of the Swampland program. That is a remarkable proposal that, when investigated, has led us to learn a lot about the moduli spaces, the geometry of moduli spaces that we get in effective field theories, and what happens with them in the physics and the geometry of them. You have already heard several talks that deal with this: Irene, Kumrum, Tom, and more. And the thing that I want to more specifically talk about is not the Swampland distance conjecture itself, how you reach this infinite distance limit along the moduli space, and there's this tower coming down and so on, but what happens to the curvature of the moduli space when you reach these regions. We already had a talk by Kunrung, which introduced this subject, so I start from the same place. This curvature conjecture that was proposed in the initial paper and which was rooted on several things. One of them is very familiar to most of us, which is this kind of geometry that we get in, for instance, when we look at the type 2B axial dilaton moduli space by itself. We get this hyperbolic geometry that has a negative constant curvature, and that satisfies the proposal of the conjecture. Not only that, we get it in other simple cases, like when we have a single Kerr modulus, and moreover, it's associated to this Kerr potential with the minus log structure that we all know and love, and that is, well, at least I try to interpret it as a string theory telling us something about how quantum gravity deals with effective field theories. But nevertheless, no. Yeah. But nevertheless, even in the richer context of Calabi-Yau compactification to 4 dimensions in extended supergravity, there were further motivation for the conjecture to be true. It was in this context, in particular by looking at the vector multiplet moduli space, that some counterexamples were found. The counterexamples not only found a a positive curvature, but actually something that diverged as you approach the infinite distance limit. So here one can do 2 things. We had a very nice talk by Kunrun saying, okay, let me take a step back and try to see some of the consequences of negative curvature, like this geodesic property, and try to see if the examples with positive curvature also satisfy it, and then try to modify the statement. But I'm going to do something else, okay? I'm going to look at this counterexample, try to understand it in general, try to understand when is the asymptotic curvature positive, when it is divergent, and what does it mean that it's divergent, both from the viewpoint of geometrical viewpoint and the physical viewpoint, and try to learn something out of it. And as I will try to convince you today, when you do this exercise, you learn something, you learn some lessons that are at the very heart of the Swampland program, that also are at the very heart of the interplay between geometry and field theories. All this work coming from geometric engineering, starting from the United States and going up to today, and we also had many nice talks about it, are also related to these questions. Okay? So let me get started. Yeah. No. Okay. Why is the distance or what? Okay, anyway, so the laboratory that I'm going to use in order to ask all these questions is the same one that I was mentioning, Calabi-Yau compactifications and vector multiplet. And in particular, I'm going to look at type 2A compactifications at large volume. So infinite distance limits that increase the volume, you always stay at large volume because they give you a particularly nice handle of the geometry and how you encode geometrically what's going on. Later on, in particular, I'm going to look at this very simple set of trajectories in which you grow one Keller modulus and you leave the rest untouched. This is a subset of models which we have a physical interpretation of in terms of 4-dimensional string back reactions, but I'm mostly using them because they are simple, and then I'm going to generalize and even go to things that are not even at large volume. So this limits, we go to large volume, we also go to strong coupling just to stay in the vector multiplet moduli space, not to move in hypermultiplet moduli space, and then we have that the distance conjecture tower is always the same. There's a D0 branes, the tower of D0 branes, essentially the M theory dimension is opening, and we have a relation between the tension of this back reacting NS5, the 4-dimensional string, and the tower of D0 branes. So the good thing is that this limit has been classified in a series of works, and actually this setup was very useful to learn many things. It was where the emergent string conjecture was initially proposed. It was also very nice to classify all these limits in terms of monodromies, and we know a lot. So we can use all this knowledge to learn something of the questions that I was telling you about. But not to pass the slide. Okay, so again, So type 2A Calabi-Yau vector multiplet sector, I go to some large volume limit, and I co-scale the dileton in order to stay in vector multiplet model space, so large volume and strong coupling. And then the classification of the limit is very simple. There is this integer w that tells you how fast the volume is growing, and that is classified in terms of an integer vector and a contraction with a triple intersection number. So you have this kind of limits in which you decompactify one dimension. You have the other one in which you decompactify two dimensions, and you end up with F theory on the same Calabi-Yau manifold. And these ones which are emergent string limits, and that most of the time you have an heterotic perturbative string dual. All right. Yeah. Good. So when you do this, because you have always the same theory circle that is growing the fastest, if you want, you also have an M theory intuition of what's going on. You can also track this trajectory in terms of M theory on the same Calabi-Yau times a circle. And what's going on in one case is that the Calabi-Yau is growing in type 2A. In M theory, if you see it from the viewpoint of M theory, the Calabi-Yau is not changing the volume, but it's maybe changing and moving the moduli space while the circle is growing, okay? And then you can understand, if you look at these three limits from the viewpoint of M theory, you can classify into two subsets. The W=3 limits are the ones in which you are in the M theory moduli space, you are moving at finite distance, and the ones that are W=2 and 1 are those that are also infinite distance in the moduli space, the Keller moduli space of M theory. Okay, so this will be useful for us because when we want to look at the moduli space curvature of type 2A, we can use the M theory intuition. So how does it work? So the first thing that we do is we write the Riemann tensor of the moduli space using this Strominger popularized formula, and implemented that we are a large volume, so we have a lot of shift symmetries. It simplifies the computation, and essentially we get a very simple formula in terms of triple intersection numbers that we then convert into a formula for the scalar curvature, okay, in type 2A. Here we have a negative piece and a positive piece. This is a definite positive piece, and this is the form that it has. You can interpret in this way, essentially a volume factor that it goes to infinity, then the inverse of these gauge kinetic functions, so essentially the gauge coupling squared, and then a bunch of triple intersection numbers. So what's going on along limits is that these things grow, and this thing may or may not compensate the growth. These infinite distance limits, what we're used to think of them is that weak coupling limits. But it could be that all couplings go to 0, or some of them don't. And this is where the fun begins. Oh, yeah. Moreover, when we express the same quantity in M theory variables, because we have the M theory intuition of the path that we are taking, we get a much simpler expression, essentially the triple intersection numbers contracted with the inverse of the gauge kinetic function. So essentially a product of gauge couplings. So a divergence will occur in M theory. Some of these guys, or all of them, go to infinity. So for instance, in W=3 limits, we are looking for a finite distance trajectory in which we reach a strong coupling, infinite coupling point at an M theory boundary, because this is a continuous function in M theory moduli space. Now, by following the classification of Witten of M theory boundaries, when you compactify M theory in a Calabi-Yau, we know that this needs to correspond to a divisor that is collapsing to a point, and then in the M theory frame, what we will be seeing is a 5-dimensional superconformal field theory. Now, if we go back to the type 2A frame where we started, we don't have a divisor that collapses. It collapses like relatively to the volume of the Calabi-Yau. We have a divisor that stays of constant volume and a Calabi-Yau that grows to infinite volume. Okay? But nevertheless, even if the volume diverges, this Calabi-Yau stays of constant volume. Which means, in terms of the effective field theory, there's a gauge coupling in the 4-dimensional effective field theory that stays constant along the limit. And this suggests there is, even if I go along this infinite distance limit, and we typically see this as some gravity decoupling limit because we have this tower that goes to 0, whatever, exponentially fast, there is always some interacting gauge theory below the distance conjecture tower, which is something quite non-trivial, that this can happen. In fact, if we use this picture and we reconsider the Lagrangian, but now we measure in units of the maximal cutoff of the four-dimensional effective field theory, which is what makes sense, then we recover the kinetic terms that corresponds to rigid n equals 2 field theory, okay? Because we need to multiply by this volume factor that translates between Planck units and maximal cutoff four-dimensional units. So the upshot is that in four-dimensional EFT units, when we measure the kinetic terms of our moduli space in these units, most of the kinetic terms diverge. And as such, we should decouple them for the low energy effective theory. But some of them don't. And this is the same statement by supersymmetry that some of the gauge couplings do not change. Okay? And this is the case that remain at least below this scale at any point in the infinite distance limit. So this is the Lagrangian that we get once we express everything in the natural four-dimensional units, like this D0 brane mass. And the dynamical fields are the ones that appear in this kernel of this matrix that we construct with the triple intersection numbers and the direction of the limit. One interesting point is that the direction of the limit is excluded. It's something that decouples dynamically from the effective field theory in 4 dimensions. Okay? And then when we plug this, we get a rigid prepotential from which we can also get a curvature in terms of the rigid effective field theory n equals 2 for dimensions, no gravity. So it's using the usual formula. And essentially, we get this y-squared function that we had before, but redshifted to the 4-dimensional scale. Okay? So to sum up, the curvature along these limits, we can approximately express it as a negative constant term plus a divergent term that is actually the Planck mass over the D0 brane mass over the distance conjecture scale multiplied by the curvature of the rigid theory. Okay? So that's essentially the summary of what you get out of this analysis. Negative term, positive term, this is divergent, and if this is non-zero, this will gain over this one. Okay? So this is essentially the picture that summarizes everything that I've been telling you. You start with scales in terms of Planck units. You get that you go along an infinite distance limit. There is the tower coming down. But nevertheless, even if the tower is going down exponentially fast, you always get some degrees of freedom here that are dynamical, that corresponds to a theory, a field theory in which gravity is naturally decoupled. That's actually the statement of the distance conjecture in this particular setup. And then you get a curvature that is of this form, that blows up because this thing, let's say, is a constant, and this thing goes to infinity. And moreover, in the examples that we look at, we have a bunch of charge states, which is going to be the field content when you go to the 5-dimensional superconformal field theory in M theory. Okay. One could do something different, which Kumprum also mentioned during his talk. One could just go along some mixed direction that corresponds to the vector multiplet, vector multiplet space, but also maybe hypermultiplet, like making the volume large without co-scaling. That would be more like the idea that the setup that people have in mind when they do this geometric engineering, and you want to take the volume and decouple the Planck mass and just keep a local patch and get a non-compact Calabi-Yau. But the story will be the same. Okay? You will have also a theory that remains below the Kaluza-Klein or whatever tower that is dictated by the distance conjecture, and you will also have this thing that blows up. I'm not going to go there. I'm going to stay in the vector multiplet moduli space, but I'm going to try to summarize all these lessons in what we call the curvature criterion, which is saying that along these directions, if you have this setup, you obviously recover a curvature that blows up to infinity. What the curvature criterion is saying is that every time that this happens is because you have a effective field theory that every time you get a infinity in the curvature, a pole is because there is rigid field theory that is decoupling from gravity. So this is the effect that generates a divergence in the curvature and nothing else. That's the proposal. Okay? So in other words, in this particular setup, the curvature divergence is sourced because there's a gauge theory that is parametrically stronger than gravity. If that was not the case, then we will not have the divergence. Okay? In our case, the decoupling of gravity and a bunch of fields that we throw away happens because of the hierarchy of kinetic terms, and I think that will be also true when we go away from this n equals 2 vector multiplied setup. And also what we need for the divergence is that the curvature of the rigid theory is equal to 0. If we have a rigid theory where the couplings do not run, where the kinetic terms are flat, then we will never get the divergence in terms of the curvature in Planck units. We also get a set of charge states. It's an interesting setup, which actually is an infinite tower. It's a very dense tower, more than a Kaluza line. And then what we also observe when you look at the computations is that, well, there are limits in which the curvature does not diverge, but they are close by to the ones that do. And so there is this y squared term. This term in here is very large. You don't get a divergent curvature, but you get something positive and large. Okay? But if you are not close to the divergent points, you always get an asymptotic negative curvature. Yeah. So let me recap. What we did is to take these counterexamples and do the general computation and identify whenever we have a divergent curvature in vector multiplied moduli space of Cannes-Lavillois for any number of moduli, blah, 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 blah. And it always boils down that the asymptotic curvature in this setup is a result of two compensating effects. One of them we can identify with a gravitational contribution, which is negative and constant. And the other one is a contribution from this rigid field theory that survives even when you go along the infinite distance limit. Okay? And this is non-negative and typically positive, and is what makes the curvature diverge. So if you want, the initial conjecture is recover when the gravitational interactions dominate over gauge ones, or they are the same strength. If the gauge interactions do not, yeah, I don't see anything, but I can, okay. When when they are of the same strength, or when the gauge interactions are parametrically stronger than the gravitational ones, is where you get when the divergence, which means that gauge interactions are winning, and you could essentially decouple the theory. Now, if this is a general feature, it could be useful to detect and to recover all the things that people have been doing for geometric engineer of field theories that are decoupled from gravity, because you would just put the curvature in your artificial intelligence program, whatsoever, and then give it the curvature of a moduli space and go see where it blows up. And then you say, OK, here I will have an effective theory that is decoupled from gravity. And you could do that for many, many cases. Now, so actually now is when things become interesting, because one can set a criterion to guess when this is going to happen. And what is the criterion about? A second criterion to make like actually numbers with this criterion. So if I have a gauge theory, then I have a natural scale associated to this gauge theory, which is the maximal cutoff that I have as indicated by the magnetic with gravity conjecture. So I have essentially the gauge coupling times the Planck mass to some power, okay, depending on the dimension. And if I have gravity, I also have a maximal cutoff, which is the species scale, the same species scale that you have heard in Dittelstock, Hirnstock, and so on, that plays a central role in the whole Swampland program. Now, what I can do in the setup that I'm talking about, this vector multiplied moduli space in 4 dimensions, is to compare these two guys and see which one is bigger and how much one is bigger from the other. If the magnetic with gravity conjecture is the gauge theory cutoff is much bigger than the gravity cutoff, is precisely when I get a divergence in the curvature. Okay? Actually, I get something like this to the power dictated by this by this scaling weight of that I was mentioning. So again, this is an indication that gauge interactions dominate over gravity. This is true for the limits that I was telling you about, these EFT string limits. But it's also true for more general limits involving growth sectors that has been very useful when analyzing infinite distance limits from general viewpoints. And they correspond to this kind of enhancement. What is more, this criterion, this way of comparing things is also independent of the dimensions. So I can apply it to the gauge coupling that is here and this 4-dimensional effective field theory, but I can also go up and look at the gauge theory or whatever effective theory that I have below the species scale. In this case of double equal 3 limits is the 5-dimensional superconformal field theory, and here this statement will also hold. So I have a strongly coupled theory that decouples from gravity here as well. And this is interesting because I can try to look at this kind of cases where the curvature divergence in terms of a set of theories, one on top of each other, of higher dimension. So let me see how that goes for other kind of limits. I'm hoping that this works. Yes, I think. OK. So for instance, for other kind of limits, the double equal 2 limits are usually understood as F theory compactify on the same Calabi-Yau. I have a 5-dimensional a tower of Kaluza-Klein states going from 4D to 5D, and another one going to 6D, and eventually the species scale, which is a 6-dimensional Planck mass. If I assume this hierarchy, where this guy has to do with the divisor that is not growing, in which I can wrap NS5 brane in type 2A or an M5 in M theory, and I have a non-critical strings. If I have this hierarchy, then I associate these sort of limits with, indeed, F theory on Calabi-Yau, on the same Calabi-Yau. So I'm going along a path with this F theory. Now, what is going on is that I have this 4-dimensional effective theory decoupling from gravity, this 5-dimensional effective theory decoupling for 5-dimensional gravity, and this 6-dimensional superconformal field theory decoupling from gravity. Actually, this path that I'm taking is realizing the geometric engineering that we all know from F theory, shrinking curves, and things like that. Now, the result is that if I only have a tensor branch, then I don't have a divergence. But if I have a non-trivial gauge group also at this level, I do have a 4-dimensional effective theory with a non-trivial curvature and therefore a divergence. So I need gauge interactions all the way up to the species scale to get the curvature. The curvature divergence is not only telling you that you have this effective field theory is decoupling for gravity, it's asking you to have gauge interaction in this context all the way up from 4 dimensions to the species scale. That's the take-home message. No? Yes. Now, I can do something a little bit different, which is taking a limit in which these two scales, the 6-dimensional Kaluza-Klein and the tension of the non-critical string, are not different from each other. They're scaling the same. In this case, something additional can happen, which if I have some state of the non-critical string wrapped on one of the circles of compactification down to 4 dimensions, and some surviving mode that is here trapped between the Kaluza-Klein scale going from 4D to 5D. This guy, if it's in here, is not up in here, is going to make a difference as it corresponds to the curvature divergence. An example that one can build is this Klein-Meyer-Buffer conifold, which is understood as this sort of vibration. Yeah, OK. But instead of taking the usual F theory limits, which would take me the elliptic fiber to be the smaller of all the curves, I'm going to take it in between. This is not the standard F theory limit. But in this case is when I have this D2 brane in here, and mix in between the Kaluza-Klein tower of D0 branes. And then I will generate a divergence a la Gopakumar-Buffer when integrating this guy out, and this will translate eventually into a divergence. OK, I'm running out of time. Let me just mention that you can do the same game with double equals 1 limits, which are emergent string limits. Here, what you get is, in 6 dimensions, a little string theory. This is a theory they have, and you have the same story. If the little string theory only has a tensor branch, no divergence, but if you have a gauge theory at this level, just below the species scale, which is the heterotic scale, the dual heterotic scale, then you have a curvature divergence. So the curvature divergence really detects gauge fields all the way up to the species scale. And finally, just a few words, you can do the same for other Cannon limits which are not large volume, which are more Seiberg-Witten limits. In here, the roles that I was telling about the hierarchies has to do with the degenerate metric that you have because of polynomial corrections to the prepotential and the essential instanton that Thomas and friends were modeling in a series of papers. And you have the same sort of a structure. OK. So the conclusions essentially are these Swampland criteria have been extremely powerful to understand what's going on in asymptotic limits in moduli spaces. And here we have focused on understanding what happens with the scalar curvature, what can happen, and what does it mean. Okay? We have focused on vector multiplet moduli space, but many of the lessons are more general. And the take-home message is you have a curvature divergence when there is an interacting gauge theory, non-trivial gauge theory, not non-running or whatever, running, couplings, and so on, below the distance conjecture scale that is parametrically stronger than gravity. Okay? Of course, in here, the relation with the curvature is because we are in n equals 2, and there is a relation between gauge couplings and kinetic terms, but the lessons can be generalized. And the picture holds in many cases, not only large volume limits, which are the easier to parameterize geometrically, it's also in Seiberg-Witten limits. And the proposal is this is the only way to generalize, to generate curvature divergence. If that's true, then we recover part of the intuition of the initial proposal, that you have negative curvature with only gravity is important. So that's all. Thank you. Oh.